So we are beginning with chapter 1, that is electric charges and field. So we will begin with the discussion first of all about the concept of static electricity. So let us begin by understanding what do we mean to say when we say the term static electricity. So basically over here we are implying that the charges are at rest. The word static is implying rest, and electricity is basically inferring to the charge. So that is, I mean to say that the charges are not flowing, they are representing charge in general. So in this we are going to study when the charges are not in a state of motion. So when we talk about static electricity, it can be observed in various ways. For example, when the clothes are removed from a dryer, they cling together because electric charges are transferred between the clothes. Or when we brush our hair, both the hair and the brush becomes charged, as a result of which the brush attracts dust or bits of paper and our hair stands on their roots. So all these phenomena are devoted to the study of electrostatics or static electricity, which is the study of charges or the electrons at rest. So let us begin with the concept of charge. So we are first of all beginning with understanding electric charge. So what is an electric charge? So charge is the property of matter that is associated with matter, due to which it produces and experiences electrical and magnetic effect. So this is how we define charge. So it is the sole cause or the reason behind producing electrical and magnetic effect. Producing electrical and magnetic effects. So whenever we refer to charge, so we define it in this way, that it is the property that is associated with matter, and it is the reason behind the production and experiencing of electrical and magnetic effect. Now we begin this discussion by first of all discussing the very nature of an atom. So the moment we discuss about an atom, we come to the three subatomic particles, and they are electrons, which are negatively charged particles, protons, which are positively charged particles, and neutrons, which are neutral particles. So we have the electrons, protons, and neutrons. So electrons is basically a negative charge having minus E, proton is positive charge having plus E, and neutrons are neutral. So over here we must mention neutrons, which are neutral. So when we talk about the least known charge which can exist on an individual basis, so we say that it is equal to an electronic charge, which is equal to 1.6 into 10 to the power minus 19 coulomb, or if it is existing on an proton, then we refer to it as E plus, which is equal to plus 1.6 10 to the power minus 19 coulomb. So this is the smallest known charge that can exist, or can have a smallest charge which is in existence in nature. So now we come to discuss about the properties of charges. So let us discuss about properties of charge. So the first thing about charge is that the charge is transferable, and that is the reason why we are going to study this chapter. Charge is transferable. Now, when we say that one charge body is placed in contact with another charge body, then we say that the charge transfer is taking place if they have different charges. Or we can also say that when two bodies are rubbed against each other, then the charge transfer takes place. Now, over here, a very subtle question can be asked, that since charge is involved with mass, every charge is involved with mass, because as I said, charge is a property of matter. So we can say that with the transfer of charge, mass transfer is also taking place. And I am also writing the second point, where we say that charge is always associated with mass. Charge is always associated with mass. And it is because that they both are property of matter. Mass and charge, they both are property of matter. The quantity of matter contained in a body is regarded as mass, and the charge is the reason behind the experiencing and the effect of electrical and magnetic effect that we observe around us. So we say that whenever charge transfer is taking place, in the subtle reality mass transfer is also taking place. But since it involves very negligible mass, we do not observe it in experience, because it is very microscopic in nature. As we know that the mass of electrons, protons and neutrons are of the order of 10 to the power minus 27 and 10 to the power minus 31 kg. So they do not produce any macroscopic effect. The next thing we say is that the charge is conserved. Now this is something which is the first thing which we are learning over here, which involves writing a mathematical equation, or which can be expressed mathematically. So if I say that we have a system, suppose I consider that there is a and then there is a B sphere. They both are identical in shape and are mounted on an insulating stand, such that initially A was having a positive charge distributed over it and was equal to, let us say, 10 microcoulomb. B was initially neutral. Now A and B both are identical spheres. Both are identical spheres. So if I rub A against B, or if I just say that A and B are kept in contact with each other and then separated, so then what will happen? Since they both are identical, the charge transfer will be equally done, and the charge transfer will be done in such a way that A will acquire a positive charge that is equal to 5 microcoulomb, and B will acquire a positive charge that is another 5 microcoulomb. Care must be taken that these two systems are kept far apart. When I say far apart, I mean to say that there is no induction taking place on the surfaces of A and B. So we say if both A and B are identical, then on rubbing A and B against each other, or I can say that A and B constitutes a system, provided they are kept on an insulated stand. So the charges of A and B is conserved. So I can say charge of A initially plus charge of B initially is equal to charge of A finally plus charge of B finally. So this is how we can write a energy conservation statement for this particular system, which involves charge transfer taking place between A and B. So over here we mean to say that the net charge remains constant even though it may not be zero. The next one is if the universe is considered as a whole, then the conservation of charge means that the net charge of the universe is also constant. And this principle also prohibits for the creation and destruction of the charged particles. However, because of the charge conservation, charged particles are created and destroyed only in pairs with equal and opposite charges. So this law is also true for relativistic motion, which means that the total electric charge of an isolated system is relativistically invariant. I am repeating this line one more time. The law is also true for relativistic motion, which means that the total electric charge of an isolated system is relativistically invariant. Or you can understand it in this way, uh, that the numerical value of the elementary charge is independent of its velocity. If it would be dependent on velocity, then what would have happened? We already know that an atom is neutral and there is a difference in the masses of an electron and a proton. And we also know that the electrons move faster in an atom in comparison to that of a proton. So if the charges were dependent on velocity, then the neutrality of the atoms would be violated. So over here I can simply say that there is an invariance of charge, or I can note it in the form of another point where I say invariance of charge. Invariance of charge. So the numerical value of an elementary charge is independent of velocity. So it is independent of velocity. However, it must be kept in mind that mass it depends upon velocity, and we have somewhere heard of this expression where we say m equal to m naught upon under root of 1 minus v square by c square. So for charge system we do not write any such equation. That we say that it is basically the law is also true for relativistic motion, which means that the total electric charge of an isolated system is relativistically invariant, or which I have explained it to you in simple language, that even though the electrons are moving faster in comparison to proton and they both have different masses, but we do not see the violation of charge taking place in an atom is electrically neutral. The next thing which we say over here is the quantization of charge. So I say that the charge is quantized, or quantization of charge. So whenever I refer to this, I mean to say that the smallest known charge is an electron. So we say that the charge of an electron is the smallest known charge, which is equal to 1.6 into 10 to the power minus 19 coulomb. And since whenever the charging is taking place, that involves the donation or acceptance of electronic charge, so I can say that the charge on any object is going to be an integral multiple of electronic charge. So I am mentioning it in this way, that the total charge on the system is equal to plus minus ne, where I say that n is an integer. It must be kept in mind that over here we are saying it in this way. Let us take understand it in this way, that suppose I am having a small piggy bank where you put your spare money, and you put rupees 5 into it whenever you are left with some change. But it should be kept in mind that you are always putting rupees 5 into it. So if you are always putting rupees 5 into it, on any fine day the amount inside it can be A 92, B 108, C 40, D 96. So in your opinion you will say that all these possibilities are not true. The only possibility that is true is 40, and it is because that 40 is multiple of 5. So similarly, when we say that whenever an object is having a charge or acquires a charge and it involves the transfer or acceptance of electron, we say that the charge on the system is equal to integral multiple of electronic charge. So that is, the charge on an object can never be plus minus 2e by 3, or it can never be plus minus 17.2e, or it can never be plus minus 10 to the power minus 6e. So all these possibilities are not true. So the charge on an object is always going to be an integral multiple of electronic charge, and that is what the statement the quantization of charge implies. The next thing that we take in mind on the last property about the study of charge is the additive nature of charge. Additive nature of charge. So when I say additive nature of charge, then I mean to say that the total charge on the body is the algebraic sum of all the charges located on the body or anywhere on the body. So while adding this into consideration, their sign must be taken into consideration. So for example, if I consider a body like this, where there are different charges over here, maybe plus 2 microcoulomb, over here minus 3 microcoulomb, and over here plus 2 microcoulomb. So if I write the total charge on this system, then it will be written as plus 2 plus minus 3 plus 2 microcoulomb, and the value will be 1 microcoulomb charge on the total system. So we need to understand that the charges are added just like real numbers. They have no direction, or we can say that charge is a scalar quantity. Charge is a scalar quantity. So now we begin understanding the process of charging of a body. So let us come to understanding the process of charging of a body. Now the process of charging involves two ways. So these two ways which we are discussing over here, the method one is charging by rubbing, and the next one will be charging by induction. So we will be having these two processes of charging. So when I say charging by rubbing, I mean to say whenever two objects A and B are rubbed against each other, when they are rubbed against each other, then some amount of electrons will be transferred from one object to the another, and as a result of which one object will become positively charged, and the another object will become negatively charged, which we can understand over here in this way, that maybe after charging A acquires a positive charge whereas B acquires a negative charge. So it must be kept in mind that the amount of positive and negative charges on A and B will be equal in magnitude. It must be kept in mind that the charges on A and B will be equal in magnitude, and it is equally important when we are rubbing these two charges, they become electrically charged by the transfer of charge, that is electrons which is transfer taking place. So over here I can give you one famous example which is generally asked, that is rubbing of glass rod with silk cloth. So if we are rubbing glass rod with silk cloth, glass rod with silk cloth, so this generally happens that glass rod becomes positively charged. So glass rod will acquire positive charge, and the silk cloth will become negatively charged. So it will become negatively charged, and it must be kept in mind that the charge on both of them is going to be equal in magnitude. That is, for example, if we say that the glass rod acquires maybe suppose 3.2 10 to the power minus 18 coulomb charge, then the silk cloth will acquire minus 3.2 10 to the power minus 18 coulomb charge. So that is the electron transferred from the glass rod will go to the silk cloth, and we can say that the glass rod will become positively charged and the silk cloth will become negatively charged. It must also be noted over here that charging by rubbing can take place in insulators. It does not necessarily involve a conductor. So both the glass rod was an example of a inductor. So we were rubbing inductors against each other. So if someone asks you, is charging by rubbing or charging by conduction or charging by friction can only take place in case of a conductor? So it is not necessarily true. When you are charging by rubbing or by charging by friction, it may be possible that the two objects involved are example of an insulator. Let us come to the next one where we say charging by induction. So now induction is a process in which a charged body can be used to create other charged bodies without touching them or losing its own charge. So it must be noted over here, without touching them or losing its own charge. So how it takes place? So now over here charging by induction takes place in conductors only. So it is important that we understand this. Charging by induction takes place generally in case of a conductor. If you wish, you can do it in an insulator, but the process is not that useful. So if I suppose that I have a conductor A which is positively charged and is mounted on an insulated stand, and if I say that another uncharged sphere B, which is also mounted on an insulating stand, is brought near it. So now what will happen? A will induce some negative charge on B, or I can say that the positive charge on A will attract all the free electrons which is present in B on the end which is facing A, and as a result of which the other end or the farther end away from A will acquire positive charge. So something like this will take place, and this is regarded as bound charge. So this negative charge gets bound because of the positive charge present in A and is regarded as bound charge. And if we manage to earth the other section or the farther end, then what will happen? The charge will vanish and the system will look like this. So A will still be having the same magnitude of positive charge, and B will be having a negative charge on one end or on one face and zero charge on the other face. And now if we manage to separate these two spheres, if we take them far away from each other, so the charge on B will get equally distributed all over it, and B will become negatively charged, whereas A will remain positively charged and have no effect on its positive charge whatsoever. So the charge on A remains invariant, whereas B becomes negatively charged because of the presence of A near it. So this process is regarded as charging by induction. So in case of charging by induction, if a question like this is asked, suppose we are given a charged sphere having a charge equal to, suppose, 10 to the power minus 6 coulomb. So is it possible to create 1,000 new charge spheres using this charge, each having value of 10 to the power minus 6 coulomb charge? So the answer is yes. So using one sphere I can create a negative sphere, and then using the negative sphere you can create positive, or using the initial one you can create the negative one, as many as you want. So we can create as many charges as possible for over here, so there is no end to it. So if the question like this is asked, you must keep in mind that charging by induction is also a possibility and can be employed in these cases. Now we move on to study the first mathematical law apart from the charge conservation statement, that is Coulomb's law. So let us begin with Coulomb's law. So it was given by Charles Coulomb, and what he observed is, so if there are two charges Q1 and Q2, so if we take, let us begin with two charges. So we are beginning with Q1 and Q2, which are separated by a distance or separation r. So there is a force of attraction or repulsion depending upon the nature of the charge, such that the magnitude of force is directly proportional to the product of the charges, and it is inversely proportional to the square of the distance between them. So it is inversely proportional to the square of the distance between them and is directly proportional to the product of the charges. And on combining these two equations, we write it in this fashion that F is equal to K Q1 Q2 by R square. Now over here we are simply writing where K is regarded as Coulomb constant. So if we calculate the value of K from here, we write K as 9 into 10 to the power 9 Newton meter square Coulomb to the power minus 2. So now we will read about K in detail. So let us understand Coulomb constant. So when we say F is equal to K, so we can write it as 1 upon 4 pi epsilon r epsilon naught Q1 Q2 by R square. So the value of Coulomb constant is expressed in terms of 1 upon 4 pi epsilon naught epsilon r. So we can say that Coulomb constant is equal to 1 upon 4 pi epsilon naught epsilon r. Now for over here let us understand what each term is implying. So epsilon naught is regarded as permittivity of free space, or we can use the term electric permittivity of free space. Electric permittivity of free space. And the another term which we have employed over here is epsilon r is called as relative permittivity, and is also regarded as the dielectric constant of the medium, or it is also regarded as dielectric constant of the medium. So this is what these two terms implies. So now the first thing that we are going to discuss over here is, so we are putting for air. So let us understand for air or vacuum. So for air or vacuum, for air also we are approximating, for vacuum it is exactly equal to 1. So epsilon r is equal to 1, and for a conducting medium, the value of epsilon r is infinity. So if we consider that the charges are placed in air for the time being, so if the charges are placed in air, so we write it as 4 pi epsilon naught Q1 Q2 by R square, and from here we obtain that the value of epsilon naught is 8.85 into 10 to the power minus 12 Newton to the power minus 1 meter minus 2 Coulomb square. So this is the unit of electric permittivity of free space, or simply permittivity of free space. Now we are going to discuss about what is this parameter all about, and how does it contribute or change the nature of force that is acting between the two charges. So if we come back to the previous page, so we are seeing that the two charges are separated by a distance r in air or vacuum. So we generally take example of air. So if the same charge setup is over here in air, epsilon r is equal to 1. So if we take the same charge setup and dip it in water, so if we dip this entire system in water, so the value of dielectric constant or relative permittivity is 80 for water. So now if we wish to write the equation of force which is acting between these two charges, so then it will be written as 1 upon 4 pi epsilon naught epsilon r Q1 Q2 by R square, or I can say that the force in water will become force in air divided by the value of dielectric constant or relative permittivity of the medium, that is divided by 80. So using this I can also define the dielectric constant of the medium. So it is the factor or a parameter, or the factor by which the value of the force between the two charges get reduced in comparison to the force acting between them when they are in air. So dielectric constant or epsilon r is a very important parameter, and this is in where we can say that the value of g, which we had in uh, gravitation constant, g m1 m2 by r square. So this value of g was regarded as a universal constant because the value of g was independent of the nature of the medium, and this is the reason why we are writing or understanding what is going to happen when the charges are dipped or surrounded by another medium. So let us come to the next point. So in the next point we say that the Coulomb's law validity. Before understanding validity, let us also understand one more fact. So when we said that the forces is k q1 q2 by r square, so I mean to say that the both charges will experience the same amount of force. Be it the first charge or the second charge, they both are going to experience the same magnitude of force, that is F12 is equal to F21, and it is equal to k q1 q2 by r square. So the magnitude of force acting on both the charge is going to be same. And if I consider that both the charges are of positive nature, so if we consider that it is plus q1 and it is plus q2, so I can say that this is repelled by each other. So this is force by 1 on 2 and this is force by 2 on 1. So over here I can say that F12 vector is equal to minus F21 vector. Or if we would have taken an example where one is negative charge and the another is positive charge. So if I take minus q1 and plus q2, then the force is going to be attractive in nature, that is force by 2 on 1 and this is force by 1 on 2. Still this equation F12 vector is equal to minus F21 vector holds true. So from here I can say that the two forces are having the same magnitude but opposite direction. So I can say that Newton's law is in accordance with Newton's third law of motion. So it is in accordance with Newton's third law, that is the two forces are having the same magnitude but are opposite in direction. The next thing that we are going to discuss over here is that the applicability of Coulomb's law. So we are going to discuss about applicability of Coulomb's law. So in the first point, we say that the Coulomb's law is valid only for point charges. So it is valid only for point charges, and it is because if the size of an object is very large or maybe large, then what is going to happen that the charges will be different on the other faces of the conductor or the object, and hence the application of Coulomb's law cannot be done. So it is applicable only for very small or the object as compared to the separation that they are considered as point charges. The next one that we say over here is Coulomb's law is not valid for distance less than 10 to the power minus 15 meter. Not valid for separation less than 1 Fermi or 10 to the power minus 15 meter. So we can say that Coulomb's law is not applicable inside the nucleus of an atom. So Coulomb's law's applicability is not there inside the nucleus of an atom. That is, it is not valid for the separation less than 10 to the power minus 15 meter. And the first point can be considered in this way, that if suppose I have a large sphere and if I place another large sphere over here such that the distance between them is small in comparison to its radius. So now what will happen? The positive charge which is distributed all over the sphere, and over here also the positive charge is distributed all over the sphere. So now Coulomb's law cannot be applied in a proper way. The first thing is the polarization will take place. These two positive charges will definitely try to induce charge on each other, and the next one is the separation between the charges at every point is not going to be same. So the applicability of Coulomb's law is not going to be done in such cases.